Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase induction motors. By solving this problem, we shall learn how to determine overall efficiency and shaft torque of a three-phase induction motor using approximate equivalent circuit when circuit parameters are given. A 415 volts, 50 Hz, 4-pole 3-phase star-connected induction motor has following per-phase parameters referred to stator side. R1 equals to 0.5 ohm, X1 equals to 1.2 ohm, R2 dash equals to 0.4 ohm, X2S dash equals to 0.6 ohm, Xm equals to 30 ohm and Rc equals to 350 ohm. The mechanical losses are 1000 watts and the slip is 4%. Using approximate equivalent circuit, we have to calculate rotor speed, stator current, stator power factor, power input to rotor, developed torque, shaft torque, efficiency and rotor copper loss per phase. Let us first write down the given data. For stator winding, resistance per phase R1 equals to 0.5 ohm and leakage reactance per phase X1 equals to 1.2 ohm. Expression for stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.5 plus J times 1.2 ohm. For rotor winding, given resistance per phase referred to the stator R2 dash equals to 0.4 ohm and standstill leakage reactance per phase X2S dash equals to 0.6 ohm. At any value of slip S, expression for rotor impedance per phase referred to the stator Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 4%, that is equal to 0.04 per unit. Therefore, Z2 dash equals to 0.4 by 0.04 plus J times 0.6 ohm. That gives us 10 plus J times 0.6 ohm. Now we shall determine equivalent impedance per phase. ZQ equals to Z1 plus Z2 dash. Using values we get 10.5 plus J times 1.8 ohm. This may be written in polar form as 10.6532 ohm at an angle 9.7276 degree. Given line-to-line terminal voltage VL equals to 415 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 415 divided by root 3, that gives us 239.6 volt. We have computed equivalent impedance per phase ZEQ equals to 10.6532 ohm at an angle 9.7276 degree. Expression for rotor current per phase referred to stator side I2 dash equals to ET divided by ZEQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 239.6 at an angle 0 degree divided by 10.6532 at an angle 9.7276 degree. That gives us 22.491 ampere at an angle minus 9.7276 degree. For three-phase induction motor, power input to the rotor Pg equals to 3 times I2 dash square into R2 dash by S. Given per phase rotor resistance referred to the stator R2 dash equals to 0.4 ohm and slip S equals to 0.04 per unit. Therefore, Pg equals to 3 into 22.491 square into 0.4 by 0.04, that is equal to 15,175.352 watt. Now we shall calculate total rotor copper loss. P copper R equals to S times Pg. Using values we get 0.04 into 15,175.352, which is approximately equal to 607 watts. Rotor copper loss per phase equals to 1/3 of P copper R, that is equal to 1/3 of 607, which is approximately equal to 202.3333 watt. Let us now calculate per phase working component of no load current. IW equals to ET divided by RC. Given per phase resistance representing core losses, RC equals to 350 ohm. Therefore, IW equals to 239.6 divided by 350, that gives us 0.6846 ampere. Now we shall calculate per phase magnetizing component of no load current. IM equals to ET divided by XM. Given per phase magnetizing reactance, XM equals to 30 ohm. Therefore, IM equals to 239.6 divided by 30, that gives us 7.9867 ampere. Expression for per phase no load current I0 equals to IW minus J times IM, that is equal to 0.6846 minus J times 7.9867 ampere. Now we shall calculate stator current per phase. I1 equals to I0 plus I2 dash. We have determined rotor current per phase referred to stator side. I2 dash equals to 22.491 ampere at an angle minus 9.7276 degree. This may be written in Cartesian form as 22.1676 minus J times 3.8 ampere. Using values we get I1 equals to 22.8522 minus J times 11.7867 ampere. This may be written in polar form as 25.7128 ampere at an angle minus 27.284 degree. In polar form, we can write stator current per phase I1 equals to I1 at an angle minus phi 1 equals to 25.7128 ampere at an angle minus 27.284 degree. For star-connected induction motor, stator current per phase equals to stator line current. Let us now determine stator power factor. Cos phi 1 equals to cos of 27.284 degree, that is equal to 0.8887 lagging. For three-phase induction motor, total input power Pin equals to √3 times VL into I1 cos phi 1. Using values we get √3 into 415 into 25.7128 into 0.8887, which is approximately equal to 16,425.3 watt. Now we shall determine total mechanical power developed. Pm equals to Pg minus P copper R. We have determined power input to the rotor Pg equals to 15,175.352 watt and total rotor copper loss P copper R equals to 607 watts. Therefore, Pm equals to 15,175.352 minus 607. That gives us 14,568.352 watt. Now we shall calculate total shaft power output. PO equals to Pm minus PR. Given mechanical losses, PR equals to 1000 watts. Therefore, PO equals to 14,568.352 minus 1000. That gives us 13,568.352 watt. Let us now determine overall efficiency of the motor. Eta equals to PO divided by P in. Using values we get 13,568.352 divided by 16,425.3, that is equal to 0.8261 per unit or 82.61%. Given number of poles of the machine P equals to 4 and supply frequency F equals to 50 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 4, that gives us 1500 revolutions per minute. Now we shall calculate rotor speed. Nr equals to 1 minus S times Ns. Given slip S equals to 0.04 per unit. Therefore, Nr equals to 1 minus 0.04 into 1500, that is equal to 1440 revolutions per minute. Expression for developed torque Td equals to Pm divided by 2 pi into Nr by 60. We have determined mechanical power developed Pm equals to 14,568.352 watt. Therefore, Td equals to 14,568.352 divided by 2 pi into 1440 by 60, which is approximately equal to 96.61 Newton meter. Expression for shaft torque TSH equals to PO divided by 2 pi into Nr by 60. We have obtained shaft power output PO equals to 13,568.352 watt. Therefore, TSH equals to 13,568.352 divided by 2 pi into 1440 by 60, which is approximately equal to 89.98 Newton meter. So today we have solved one numerical problem on three-phase induction motors. By solving this problem, we have learned how to determine overall efficiency and shaft torque of a three-phase induction motor using its approximate equivalent circuit when circuit parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.